Okay, well, thanks to the Parker Solar Probe colleagues for helping to set the stage. So I have one slide summarizing the plasma physics, and then there will be a brief return to this, but a theme of this talk is that understanding the subset of FRBs that are repeating is connected with other aspects of the problem besides the emission mechanism, namely the long-term evolution of the magnetic field in the magnetar. It's connected with how a magnetar might produce a relativistic nebula. It's connected with how they might interact with other stars. But anyway, the starting point is a large amplitude electromagnetic pulse, and inspired by our knowledge of the solar wind in part, one will consider the possibility that there's a broad spectrum of current perturbations that's carried out subluminally with that pulse. So it's loaded with electron-positron pairs, a high compactness during the burst emission from the magnetar, leading to a quasi-thermal electron-positron distribution. And when a shock is formed in this pulse, there's an elementary mechanism for converting those subluminal to superluminal modes, which is simply that the curl of B increases more strongly behind the shock than does the conduction current, and there's a source for the parallel electric field, and you get a Langmuir ordinary wave. So with a spectrum of seed current perturbations inspired by models of alphanic turbulence, you can expect an efficiency of 10 to the minus 3, 10 to the minus 4. And self-consistently, the spectrum can extend to high enough perpendicular wave numbers that the observed frequency would be in the gigahertz range. So there are constraints on the surrounding medium from effects like induced scattering. So a quick summary of where we're going. A magnetar may stop being active, but its magnetic field may remain frozen into the superconducting core. Magnetars can interact with other stars at a considerable rate if they're residing in dense star clusters, and as a result form binaries, as a result receive mass from the companion and significantly slow down. And importantly, when they do accrete mass, the mass flowing onto their surfaces can behave in a qualitatively different way than it would in an ordinary X-ray pulsar. So how would the magnetic field freeze in? Just one quick slide about this. In the biggest magnetar flares, one thinks that the magnetic field driving the flare, the imbalances driving the flare, may originate in the liquid core of the neutron star. And the transport of the magnetic field through the core is mediated by beta reactions, and those are very strongly temperature dependent. So models of magnetar magnetic evolution and cooling show that when, with some delay, and maybe at an age of 1,000 years or a bit more, the neutrons in the core pair up, then the neutrino emission from neutron-Cooper pairs greatly increases the cooling rate, and the beta reactions essentially freeze out. So this is a thumbnail sketch of how, at much greater ages than 1,000 years, the magnetic field in the superconducting core might essentially remain frozen in. So we observe some LMXBs and old remnants, transient low luminosity LMXBs in globular clusters, and there's every reason to expect that a magnetar in some context, like dense nuclear star cluster or globular cluster, could experience binding by tides with a main sequence star or collision with a red dwarf star and then form a binary. And if at some point the the magnetar accretes at a near Eddington rate, then it can build up a substantial mass corresponding to a significant gravitational potential energy in its polar regions. So why this is an attractive scenario for repeating FRBs is that, well, in one case, we see a globular cluster counterpart to a profusely repeating FRB. We do see bright synchrotron counterparts, which have been interpreted as a rapidly spinning down protomagnetar, but which are also in their spectra consistent with low luminosity AGN. And black holes of mass of around a million solar masses or less are typically associated with dense nuclear star clusters. There are one and perhaps two evidences for periodic windows of emission in repeating FRBs. And somewhat surprisingly, even though these repeating FRBs can produce tens of thousands of bursts over hours and days, there's never been any convincing detection of periodic modulation of the pulses. Whereas by contrast, for example, our RAT, a spastic pulsar with a handful of pulses, will reveal its spin periodicity. Okay. So there is an implication there that the spin may be quite long. So just quickly some order of magnitude numbers. If the magnetar were to accrete at about nearly the Eddington rate, then you would expect its magnetopause to extend to about 10 to the 11 centimeters, and the time for equilibration of the magnetic field, when it's slowed down to the point where the rotation rate is comparable to the flow rate across the magnetopause, the time to equilibrate is quite short, and the spin period is quite long, about 10 to 5 seconds. Interestingly, one can compare the energy released in a giant magnetar flare with the binding energy of the gas to the companion, and if the companion were a fully expanded giant, then the two energies aren't too different. So that shows how energy released from the magnetar could significantly modulate or stimulate or suppress mass transfer. And in fact, what we'll be interested in is what happens when the mass transfer, say, just in the form of a stellar wind, in fact, just the mass loss from the companion in the form of a stellar wind drops to the point where it doesn't transfer to the magnetar. So if indeed periodic modulations in the burst emission are reflective of binary motion, then of course this raises the issue, well, what can one learn about the emission process if it depends on the presence of a binary companion? Okay, so obviously if the companion is emitting a wind, then that can provide target material for the shock emission process I outlined on the first slide. Well, so the main thing one deduces when one extends the theory of polar accretion columns from ordinary X-ray pulsars to 10 to 15 Gauss is that if indeed the mass can can build up in a inhomogeneous way to the point where the hydrostatic stress is nearly balancing the full Maxwell stress, then you find that the density at the base of the accreted layer can become high enough, near neutron drip density in fact, that it will form a solid. And so there's an interesting possibility that there's an interplay between hydromagnetic instabilities like the current filamentation instability, which you can see reviewed on the previous slide. Now that isn't, what am I doing? Sorry about this. Oh, here it is. filamentation instability you can see on the previous slide, and elastic instabilities in the solid layer. Okay, so what would the time scale for a magnetoelastic instability in the polar cap be? Well, the simplest estimate would be the time for a shear wave to cross at about this density of 10 to 13 grams per cubic centimeter across the polar cap. And you can compare that time scale, which is several milliseconds, with the duration distribution of FRBs in a repeating source. And you find that, well, there may be a simple physical explanation in this model for why the time scale is somewhat longer than in non-repeating FRBs. When one looks at the distribution of intervals between radio bursts in repeating FRBs, there's a clear pattern that's emerged where there's a short period, a short interval peak, probably associated with the engine just emitting yet another burst, and then there's a longer duration peak of about 100 seconds, which deserves an explanation, and one does emerge when one considers how a propagating electromagnetic pulse could emit a radio pulse without the radio pulse being absorbed. Okay, so the picture here, just to summarize, is that you have, after some period of mass transfer, where mass has built up in a polar region, the rate of mass transfer slows down dramatically, maybe to a point where, well, the rate of mass loss from the companion slows down to a point where perhaps it's not much larger than the rate at which the sun is losing mass. And then the energy stored in the polar cap continues to be released at a more gradual rate. So 10 to 35 ergs per second would be typical of a quiescent magnetar. That emits, say, a steady stream of Alfvén waves. And those propagate far enough out that their pressure can begin to exceed the dipole pressure, combing out the magnetic field into a split monopole. But the energy released by the magnetar can't just escape through the stellar wind at the speed of light. And so you form a cocoon, as you would in a pulsar moving at high speed through the interstellar medium. And then there's some magnetopause between that accumulated wind material and the outflowing material. So numbers, just to stick in some numbers then, the Alfvén radius for a luminosity of 10 to 35 would be about 10 to the 10 centimeters, the magnetopause factor of 30 larger, and then the Clarion radius might extend out to an astronomical unit or more when the mass loss rate of the companion slows down. So then just let me quickly summarize where the process of shock-mediated mode transfer would most favorably occur. So you have a pulse, say, of luminosity 10 to 42 ergs per second, which is running into the Clarion material. This is relativistic stuff with a pressure comparable to the pressure of the wind from the companion star. And then that reverse shock would complete its motion through a shell of a duration of a few milliseconds at about an AU separation from the magnetar. The shell is thin, so its Lorentz factor continues to increase beyond the fast magnetosonic value in proportion to the 1/3 power of the radius. And at this reverse shock radius might reach 1,000. Now, a key point as regards the radio emission, since this is expected to be most powerful around the plasma frequency, is that, again, the density of pairs near the base where the pulse is emitted, so at some reduced Alfvén radius due to the higher luminosity, is expected to be regulated by electron-positron equilibrium, and therefore there is some mapping of frequency with radius. Okay, so in the frame of the observer, in the contact region, you might expect this Lorentz-boosted plasma frequency to be a few hundred megahertz. And then there are constraints nonetheless on whether the Langmuir ordinary mode produced as the pulse passes through the reverse shock could escape the effects of induced scattering within the material that's being ejected from the magnetar. So that has a well-defined density. And so one finds that one may need to be a little bit above the plasma frequency in order for the wave to escape. So there are some encouraging trends one expects in this simple model. The plasma frequency will decrease as the pulse expands. And then in answer to the criticism that's been raised about narrowband radio emission at a large radius from FRB source, this wave, these Alfvén modes that were excited by some chaotic motions close to the magnetar have been stretched out in the wind. Okay, K perp in the frame of the observer doesn't change. K parallel drops as one of the radius. So you have a nearly locally planar wavefront being created right behind the shock. And that means then that the off-axis emission will be substantially reduced at a given frequency compared to what you get for isotropic emission in the relativistic frame. Okay, and then as regarding repetition intervals, and there are some encouraging possibilities. The time you're depositing a lot more energy than it was in the energy of the polarion when this one burst of energy 10 to 39 ergs is released. The time for the polarion to reform, if the luminosity of the magnetar drops back to quiescence, is about 1,000 seconds, and that's not unreasonable when you compare with the duration distribution I showed earlier. There are also possibilities of magnetic relaxation. So to summarize, this approach most definitely has observational implications in tests. You should expect to be able to see magnetars with very strong magnetic fields. If they form in neutron star binary in spirals, then the implication is there should still be 10 to 15 Gauss there helping to seed your MRI when the two neutron stars collide. Okay, that's an important consideration for the production of a short gamma ray burst. Repeating FRBs, we're going to get great sub-arc-second localizations for the new sources to be discovered, and they should be associated with dense star clusters. Again, a nuclear star cluster should work quite well, and so non-thermal radio emission may have nothing to do with rapid magnetar spin down. And yes, as we've heard, there have already been in the literature some considerations of the production of large rotation measure in the wind from a companion star. Of course, an accretion flow onto an intermediate mass black hole would also do that. Polarization swings, rotation of the magnetic field in the wind is a natural possibility, and there's no reason for the expected high linear polarization to necessarily maintain a fixed duration. So thank you. I'm sorry for going over a bit.
Very interesting talk. Okay, so we have time for some questions.
So when you have K perp ahead of the shock and no K parallel, so it's very well collimated signal after the conversion, but still there is a spectrum over K perp.
Yes, that's right.
And so is there any reason for that spectrum to have to be narrow band?
No, not at all. And so you would expect to then have a low frequency cutoff from absorption, or maybe from the plasma frequency, right? And but whether this is at any given point in the outflow a very simple power law-like structure in Fourier space, or whether it's lumpier, I think is an open question. So, but good point, yeah.
Other questions?
You have quite a few ingredients. I'm not sure I got the thing. One of the ingredients is that you have accretion onto very highly magnetized thing.
At some phase, yes.
So that you can hold up to this thing to very deep trigger starquake.
Yeah. So
do you worry that this thing may be unstable, MHD unstable? You cannot hold up.
So it's an unsolved problem, exactly how fast the material spreads. You know, again, the magnetopause is so far out that material falling down from that radius will be on a very narrow patch, okay? Right. And so I've made an underlying assumption that it will spread. Yeah. But that there will still be some angular distribution of the settled column of material.
Maybe another quick thing. So you mentioned this bimodal period distribution of
the
FRB duration, millisecond versus seconds, long. What is your story? How do you get two populations?
Well, okay, so this is, look, I mean, for those of you who haven't seen this, this is brilliant data from the FAST collaboration that was buried in a paper that they didn't choose the best title, in my opinion. It had something to do with magnetar physics, and you know, it was the data just stands out on its own as really exciting. But anyway, so what one observes in 4 different FRB sources, and then the galactic magnetar that produced the FRBs, well, let's hold off on that for the moment. So again, the repeating FRB events tend to be a bit broader in time than the one-off events, apparently one-off events, several milliseconds. There's a distribution, right? So you see a peak here between around 10 to the minus 2 seconds or so. Well, you know, okay, whatever was doing the burst did another burst very quickly thereafter, right? And the interval was then essentially determined by the same physics as what determined the width of the initial pulse. And then there's a dip, and then there's another peak ranging from 30 to 100 or maybe a little bit more seconds. And so something is either suppressing the emission of another outflow from the engine, or something is suppressing the transferred radio waves when the outflow dissipates, okay? And so the idea here was that it's the second option, and that we see when you build up a much bigger pressure with the outflow, okay, that corresponds in the self-absorption model to raising the ambient pressure of the stellar wind, right? Back to the point where the self-absorption would kill the emission. So there's an implication that then the engine has to really drop down in luminosity significantly until the next burst. Okay. So there has to be a large excursion in luminosity for that to work.
Okay, thanks, Chris. So we are at the end of the allotted time. So let's thank Chris and all the speakers this afternoon again.